Afternoon, everybody. Thanks for joining back in for the second part of Michael Sinatra's talk on segment routing. If anybody did miss the first part, it is posted in the YouTube channel, uh, and that has sort of the basics and the little bit of information that would probably be relevant for what Michael's going to go over today. But I will turn it over to him so that he can get started.
Okay, thanks. Um, as usual, I see so many colleagues, old and new, that of course I know that I have to do well here because I'm very capable folks who are able to call me out when I'm getting things wrong. So um, I like to call this the road taken 10% of the time, or stupid segment routing tricks. The first one is an ode to Robert Frost. The second one is an ode to David Letterman. I gave this talk in Boston, a shorter version of this talk in Boston at Internet2 TechEx 24. And that talk that I gave inspired me to do last week's talk, which was really sort of a background on segment routing and some of the things you can do with it. And so at that talk, we talked about SRMPLS and really how it works versus SRv6 and why you might choose one or the other, how SRISIS integrates with existing IGPs. And it's important for me to emphasize there that it also works very well with OSPF. So SR OSPF is the piggyback version of SR onto OSPF. And that works very much the same way that ISIS works. So you don't have to be using one or the other. You can use either one, actually, I should say. And so we started to touch a little bit on traffic engineering and SRTE and some of the things you can do with that. And we'll talk more about that today. And we also did some introduction to some of the node SIDs and a little bit of adjacency SID. And we did our use case, which is to do BGP next hop resolution for most of our traffic in the case of ESnet. And I showed you some of these screens where here you have an example of a packet, a NetFlow packet, where we're actually sending it out to a router. This is the node SID that's doing it. And I showed you how that goes to a particular router. And then I left you with this cliffhanger, which is what happens when you have these two node SIDs? What's going on here? Okay, what's happening with that one? So we go to our thrilling conclusion, except for the fact that this isn't really the conclusion because we're not actually going to use a controller here. You might be thinking, oh, this is great. We're going to finally use a controller. And no, we're not going to use a controller. Part of the point of this presentation is to show you that you can do interesting segment routed traffic engineering things without actually having a controller. So maybe for some episode in the future, we'll have a controller, but ours currently isn't working yet. And by the way, our experience isn't unique. It's actually, these controllers are a little bit wonky. So I think the next innovation that's going to happen in segment routing is going to be building new controllers that are sort of lighter weight and more open source, kind of like what happened with NetFlow, where we built lots of controllers that did a lot of the special sauce there. So, um, okay, so let's sort of back off and say, why would you ever want to do traffic engineering? If you're on a college campus, university campus, you may have remote offices or sort of a metro campus, or you might have like the big campus over here on out in the countryside with an administrative office park nearby, and then you've got like your medical school or something else that's way down in town, and you may have different paths to get there. And there may be some reasons why you might want to take this path, even though it's two hops over this other path here. So it's just one of those things where, like, you might want to have different ways of getting there, or you might actually want to use, you might have this lower bandwidth backup path, but you might still want to use it a little bit of the time and then use these other two most of the time. So there might be different reasons that you would want to do traffic engineering. And obviously, if you work for a regional network or a statewide network, you may have different paths across your state or up and down your state, depending on the orientation of your state, whether it's a north-south state or an east-west state or a big rectangular state. So you have different redundant paths across that, and there may be different hop counts across those or different things that you might want to do. You also just might want to understand this. And understanding networks that do traffic engineering because your regional network may be doing it, or Internet2 may be doing it, or ESnet may be doing it. If you're using LHC1, then you're using ESnet's, in some cases, traffic engineered networks. So that's actually fairly important. And if you're using LHC1, you may see trace routes that look like this, and you understand what the hell is going on, especially once you get around to hop 10 and things start splitting apart and separating away. And now you start seeing all of these different hops, and we're all going to the same destination. So we're going to the perf sonar node at CERN. Why do we have all of this exploding hop down in these teens over here? And so how does all that work? And if you actually make the mistake of running traceroute minus E and you see all that label information, you might want to try to make sense of that. We did a little bit of that last week, and I showed you how to actually show it in a little bit better formatting as well, using tools like MTR. So we'll do a little bit more of that. But I do want to say, like, when I make really complex trace routes, it is sort of a somewhat sadistic side of me that does that. But I also feel like traceroute's a really important tool and a really useful tool, and it presents a lot of subtle information that can be very easily misinterpreted. So one of the things that I like to do is sort of explain to people what traceroute is really telling them. And when you have these really complex traceroutes, that becomes more important. So I kind of like to make sure that people understand what that tool is actually telling them, and in some cases, what it's not telling them. Standard disclaimer, I do a lot of Nokia and a little bit of Juniper here. These are platforms I know, not necessarily platforms I'm endorsing. So, couple principles. Traffic engineering is like a band-aid. That's sort of my analogy. It's maybe a little more like stitches, but it's sort of like a band-aid. It's something that you do when you need it. It's a useful tool. We do say band-aid as an epithet, and oftentimes that's because the analogy we're using is you're putting a band-aid on a broken leg, which is not the right tool for that task. But in the case of traffic engineering, often a band-aid is really the right tool for the task. If you've got a cut on your hand, you don't put yourself in a body cast. You put a band-aid on it, or maybe you get stitches. And that's really what traffic engineering is. It's sort of filling in individual gaps and things like that. That's sort of the philosophy that I'm taking here, is only do traffic engineering where you need it. And 99% of the time, you're not going to need it. Shortest path works just fine. And in some cases, you may not even need traffic engineering. You may just simply need to add more bandwidth. And that's still a thing. That still works. I've been doing this for 28 years, and everyone says you can't throw bandwidth at the problem anymore. But the truth is, for all 28 of those years, we've been able to, at times, throw bandwidth at the problem. In some cases you can. So in some cases, you do need to use traffic engineering, but bandwidth may be the answer in some cases. So a couple more principles, and this is from a book called Segment Routing. What they really talk about here is the fact that one of the things that segment routing helps support is traffic engineering only where you really need it. Okay, and again, it's the same thing. What he uses is the analogy of the raincoat. You only wear a raincoat when it's raining. And what I like to do is use the analogy of the Band-Aid, and more importantly, in the world of network engineering, where we like to make up goofy sayings about things, Band-Aid's not body casts. That's going to be the watchword, the key phrase here, and you're going to hear me use that over the course of this. I personally think it's awesome. Okay. And I think, again, segment routing works very well with the idea that you only do traffic engineering where you need it, because as you build paths through your network, it takes advantage of a lot of your underlying infrastructure, like ECMP. And so if you've already got ECMP in your network, it works really well. You can do a mix of strict and loose paths, and it really works like strict and loose paths under the covers. It turns out that RSVPTE, you can do the same thing when you specify it, but when RSVPTE builds a path, it actually builds an explicit path across the network that doesn't take advantage of any underlying ECMP that you may have. It's very important for ESnet because you can see here is our link, here's our network map. Each of these links is actually n by 400. So you see these big, thick lines here, and it's really multiple thick lines that are multiple 400 gigs. And we take advantage of that with ECMP. Why do we use ECMP? People have already asked me this question. I know I kind of gave a teaser last week saying, go ahead and ask me offline. People ask me offline, so I'm going to answer it now. Basically, we do support lags for customer connections and for peering connections, but for backbone, we use ECMP. And the reason for that is it allows us to pretty easily move things into and out of our ECMP groups without having to renumber them or number them or denumber them. If we put them in lags, then we'd have to do a little bit more configuration work to pull them in and out. So this way, all we have to do is change, IGP costs, and all of a sudden, the for a particular sublink of an ECMP group, and all of a sudden that link is effectively out of the ECMP group, and we can use that for other services if we want to, like, for example, L2 VPNs or specific L3 VPNs where we only want them to take one subset of our links or have them maybe have dedicated bandwidth or things like that. And we've been using this technique since ESnet 4, and ESnet 4 was designed before I even got to ESnet. So it's been around for a while, but it still works very well for us. So in order to take advantage of ECMP, we add entropy labels to our MPLS packets. That's because Nokia, you can configure a Nokia router to look into the inside of the MPLS label stack and actually look at the IP and port information. So essentially the flow information to try to do your balancing on flows. But we actually just put entropy labels in there, which are also based on flows. And that way it just hashes across those entropy labels. So it makes it really easy to configure individual links to be in part of ECMP groups. And it works really well for us. And it allows us to actually do that combination of strict and loose paths that actually really work under the covers. So if you look at Redux of last week, we're going to start talking more about adjacency SIDs, but we're still going to be using node SIDs here. So we'll still be using those sort of loopback addresses, but we will be using adjacency SIDs a little bit more as we go on. And in defining the adjacency SIDs, this is where we make use of the SRLB, or the local block. Adjacency SIDs are local to each router. You can make them unique across your network. And ESnet has made the decision to do that in a way that's sort of future-proofing the network, so that if we wanted to do something a little bit different where we're programming the network with a controller or programming the network without a controller, it's a little easier to do that if you have unique adjacency SIDs across your network. And more importantly, it's useful to do it if we have static adjacency SIDs, because if you don't configure static adjacency SIDs, your router just picks numbers out of its reserved portion of its reserved MPLS stack. And what that means is when you reboot your router, the adjacency SID changes. So if you got anything programmed with labels, programming packets, and then the adjacency SID changes out from under you, that's going to create problems later on. So we actually want to keep it the same way throughout the network and make sure that we understand what our sort of SID to IP address mapping is. Now, remember, the adjacency SID refers to something that is specific to the link, like an IP address on an individual interface, and the node SID is equivalent of the loopback of a particular router or node. You saw this last week, and I said really the only thing you need to configure in MPLS is just the global block, which is this SR labels in Nokia speak. And what I've done here is I said you didn't have to configure this part, but now I've actually put it in. So we actually have this SRLB, which allows us to set aside another set of labels that we're going to use for our adjacency SIDs. And then we add that into our segment routing configuration down here. So we have the global range, and then we have the SRLB, and that's what's going to be used for our adjacency SIDs at this point. And the way we configure it is, this is the ISIS configuration for this interface. So here we've set the ISIS metric on it. We're doing all the other ISIS stuff, and all we have to do now is just add the adjacency SID. So wherever in your router you configure your ISIS or your OSPF parameters, that's where you're going to specify your adjacency SID. If it's under the interface itself portion, or if it's under protocols ISIS or protocols OSPF, that's where you're going to do it. And once you do that, here is the detail view of the adjacency that's formed. And you can see there's the IP address of the neighbor, and this is the adjacency SID that's added to this. So that, again, this is the same one here, Sacramento CR6, that goes between Sacramento and, in this case, LBL. All right, so here's a use case. Speaking of Sacramento and LBL, I'm going to show you an interesting use case. This is a fairly simple one. This is the Great Western Divide. It's this little driveway called Perlmutter Road. It's named after Saul Perlmutter because he won a Nobel Prize, so they name a street after you. And this is at LBL. And in this complex, LBL has a router, and ESnet has a border router, basically a PE router that connects to that border router. And in this building over here, which this one over here happens to be where I work, that also has a border router and also has an ESnet PE router. It turns out if you're a packet and you're in this building and you want to go to, say, Comcast, so anyone on Comcast, even if they're in the Bay Area or wherever they are, you're going to go to Denver to get to Comcast. And in this building, if you're a packet, you're going to go to Sunnyvale. That's if you follow regular IGP costs. Now, why is that? You might think this is the Great Western Divide, but this is really the Great Western Divide. Well, if you look at the way IGP costs work, if you have multiple hops, IGP will add your costs together. So in this case, ESnet has a latency scaler, which is 10, I don't know, what do you call these? IGP cents, okay? 10 cents of IGP cost. And then we have this bigger bandwidth scaler. And the reason the bandwidth scaler is rather large is because you want to keep your network future-proof. So you want to be able to maybe support multi-terabit links or 10 terabits, 100 terabit links, whatever we eventually go to someday after I'm retired. And so as a result, you have this rather high bandwidth scaler. And that's a little bit of a problem because at each hop you add both the bandwidth and the latency scaler. Now, the latency, it makes sense to add it together. The bandwidth, it doesn't make so much sense to add it together. So as you can see, if we had a link just between R1 and R3, it'd be 720. But if we had the cost between these three routers, as it turns out, if you have three hops, it's actually 1420 instead of 720. So that's the problem we run into. And because when we designed ESnet 6, we decided at every sort of ROADM stop, we're also going to have a router. And the idea there was that it made, the idea of having this programmable data plane, this programmable network, meant that having routers at each of these locations means that the granularity of what we can program into the network is really good. But in some cases, it means that the IGP costs can get a little out of whack. And here you can see, here is a schematic of ESnet 6. And you can basically see here at LBL, we've got two routers because we've got two optical nodes. And if you're at this router, this is the one that was in the sort of northish building that I showed you, to get to Denver, which is where we have a CenturyLink drain, and that connects us to Comcast. And over here in Sunnyvale, we have another CenturyLink drain. So to get to Denver, it's 1, 2, 3 hops. And to get to Sunnyvale, it's 1, 2, 3, 4 hops. But if you're at this router down here, which is just across the street, as I showed you, and you want to go to Denver, it's 1, 2, 3, 4 hops, but it's only 1, 2, 3 hops down to Sunnyvale. So you can see where the issue is. This little link right here becomes the Great Western Divide from the standpoint of a network engineer. All right, so how do we deal with that? Well, one way to do it is to create a segment routed tunnel. And by the way, people notice this, by the way. If you're like going one direction and you're going to your home network and you're trace routing and you're like, oh, I went through Denver to get to home and my home is in North Berkeley, then you're going to get some complaints about that. So the way we ended up dealing with it is let's build a tunnel that makes it look like this hop isn't really here from the perspective of this router right here. Okay, so that's what I'm going to do. I'm going to build a tunnel that does that. So I create a loose path. Why do I create a loose path? Because it's going to make it to the router that I want to go to, which is Sunnyvale anyway, and I'll show you how that works. But I also don't want it. I want it to take advantage of all of my ECMP links that are in between there because there's 3x400 at each of those hops between LBL and Sunnyvale. So what I do is create a loose path and I assign it a metric of 2140. Those are the two important things that I've done. The rest of this we can talk about later. And so when you actually build this tunnel, what happens is the router adds, as part of the LSP template, it automatically adds the destination on it because I specify in a filter what the destination is. This is the loopback for Sunnyvale. You'll see this is all IPv4. I explain why that in a second. And then what it does is it resolves that to a node SID, which is this one right here, 425.480. And so when it encapsulates that in the packet, that's all the packet has. It just has that 4285 425,480. But what you're going to do is it's going to give it that metric that I gave before, which is of 2140. When we go to our BGP tables, and I realize these BGP tables are a little bit complicated because this is BGP VPN route. So you're going to see a route distinguisher, which again looks like an IPv4 address. In this case, it's not really, it's an IP, it's a route distinguisher. And then you're going to see the route afterward, which is 2601/20. That's an IPv6 route for Comcast's IPv6 block. Okay, so at that point, you can see here that this is Denver 170, and you can see that has a lower IGP cost than 172, which is Sunnyvale. So normally the tiebreaker would be that lower IGP cost, and we'd send all that traffic off to Denver. However, when we actually resolve the next hop using the SRTE tunnel, it applies that metric that I gave it of 2140. You'll notice that the metric of 2140 is 700 less than the metric of 2840, which is what comes from the IGP. I just wanted to take that hop out of the picture, so I subtracted 700 from it, which gives it a very reasonable metric of 2140. And that means that when we program our FIB, we program in with the tunnel and the destination of Sunnyvale, which is this 172 router. Okay, now, so that's great. That works. That means our FIB got programmed the way we wanted it to. The traffic's now going to go to Sunnyvale while it's IPv4. Well, it turns out I made a decision about 10 years ago to use multi-topology ISIS. I thought it was a great idea because it meant that we could selectively turn off IPv4 in parts of our backbone without black holing traffic. So we could actually turn off the IPv4 control plane and actually use the IPv6 control plane and still route all of our traffic through because, again, we're using multi-topology, and that gives you a little more flexibility in how you run your different address families. But it turns out, although the SR-ISIS standards specify that you can do SR over both topologies in a multi-topology ISIS environment, for a long time, Nokia only supported it in topology 0, which happens to be the IPv4 topology, not topology 2, which conveniently happens to be the IPv6 topology. Turns out a gorilla that weighed even 800 pounds more than we did decided to tell Nokia that they wanted this feature to be added. So Nokia did finally add it in SROS 23, and we're going to go to SROS 24 later this year. But for now, we have all this IPv4 crap lying around because essentially we're encapsulating IPv6 into our IPv4. We'd actually like to do the opposite. Okay, so and it's not like we're encapsulating into an MPLS packet, not into an IPv4 packet. But what we are doing with that MPLS packet is using IPv4 as the control plane. We'd like to actually make it so it's IPv6 as the control plane, and we can't do that until we upgrade and get the multi-topology ISIS working correctly. So that little sidebar aside, let's compare this with what we're doing with RSVP. And if I were to build the same tunnel with RSVP, and I've done a little bit simpler configuration, I haven't included the SBFD, and we're going to talk about that later. But I do the same thing. I do a path loose that just doesn't go anywhere, and then I create an LSP that says, pick Sunnyvale as your destination. So build a tunnel to Sunnyvale over a loose path. And this is what RSVP does. Now compare that again with my and again, this is a little bit different because I'm using a template instead of a regular LSP, but it's the same principle. Same thing with segment routing. So this is what it looks like when I do it with segment routing. You can see it just resolves the final hop and builds a tunnel with one label. Look what RSVP does. It builds an explicit path, even though I'm not telling it to build an explicit path. It builds an explicit path according to the shortest path IGP metrics. It builds an explicit path over to Sunnyvale, but it does all these label swap operations. Each of these hops in this 134, 55, 56, 57, and 58, those all represent specific links in the 3x400. So what happens is, although if one of those links goes down, RSVP will fail over to the other links. As a regular course of traffic flow, it's not going to use those other links as ECMP links. It's going to pick one and go over it. And if that link goes down, then it'll pick another one and send all the traffic over that. So for that reason, RSVP isn't the ideal protocol because it's not taking advantage of our N by 400 links. And that's why it's nice to have SR, which is ECMP aware. Okay, so the truth is it works great. Now, you might be saying, well, you're doing that for BGP next hop resolution, and that's for things like Comcast, which you get to via CenturyLink, and you have all this IBGP running in your network. I just run an enterprise network, and I don't have IBGP running through all of my routers. I may be running in a few routers, and then I have a core that has ISIS or OSPF running. You can still take advantage of this if you have a use case where you need to have a multi-hop path look like a single hop path, like I just showed you here. You may be able to do that by using something called IGP shortcuts, and that allows you to use your tunnel table for a Nokia or iNet.3 or iNet 6.3 if you're a Juniper customer. You can do that to resolve IGP routes. And it sounds pretty wacky, but it actually works really well. And think about it, it's not really that different from saying, I'm trying to get to a loopback interface. Instead of telling me how to route to that loopback interface, you just tell me how to route to a number that represents that loopback interface. So it's really the same thing. It's just a number, a SID number, instead of an IPv4 or IPv6 address. So you can still do that. I'm going to move on to another problem statement here, or another use case. And this is a little bit more involved, and it's going to involve using strict paths. So, or at least partially strict paths. So back in 2022, our transatlantic connectivity looked like this. And these are all 100 gig links. You can see they have different hop counts. There are some links that are shared in some cases with near, and there are some links that are used entirely by ESnet. These are all lit circuits, okay? And then we have this European ring, and these are all 2 by 100 gigs. These are all 1 by 100. So you can kind of see what we're doing back in 2022. And this is just text that showed you the map that I just showed you. But if you look at the hops again here, basically you can see where from some of these Chicago and New York areas, this Boston to Amsterdam link was very hot and very commonly used. And from like the West Coast and the Southwest and the Southeast, this Washington to CERN link was commonly used because, again, it skips over a bunch of hops. It's an expressway that skips over a bunch of hops. So we had that problem. We also had another problem with that fractional near link, that portion of the near link. We would either hog it or we would use none of it. We wanted to be able to use some of it and not all of it. We wanted to be able to share it. So that was another kind of use case that we needed to manage. And so basically balancing traffic in sort of a non-standard way was what we were trying to do here. And then we had another issue that came up, which also called for non-standard balancing, which is we're going to get a new 400 gig link. And these people on my optical team, Kate Robinson and Mike Blodgett and Nathan Miller, they're all rock stars. They're all the leads of the optical team. I'm in the core routing team, so they do magic that I don't even understand. And I basically looked at them and said, this is great. We're doing this. Now I have to figure out a way to get traffic over this. But more importantly, I can't have all of the traffic going over that link, because if I do, I'll end up oversubscribing these backhaul links that go to between London and CERN. Now, it turns out those are all upgraded to 400 gig now, but at the time they weren't. So I need to figure out, how do I continue to balance traffic across these links? Also, I want to do that anyway because we're paying for them. We might as well use them. And so I wanted to be able to have more traffic over this link, but still some traffic over these other links. And it's really hard to do that with IGP costs. Also, with all the differences in topology between where those links leave the US and where they enter Europe was also another problem. So it was just really kind of messy to do. And that meant that messing with IGP costs was really going to be hard. And plus, redoing your entire IGP costing algorithm takes a lot of time and requires a lot of simulation and a lot of other things to figure out, like, where are you going to end up with collateral damage? Where are you going to end up with problems? It is a huge undertaking to try to do that. And if you're just putting a new link into production in one part of your network and you've got to redo all of your IGP costing mechanism for that, that doesn't scale very well. So clearly, when we wanted to do this shovel ready 2 years ago, doing our IGP costs isn't going to make it very easy. And there's a technology we could have used called flex algorithm, which again, that allows you to build an entirely separate IGP topology that might be based entirely on latency, or might be based entirely on traffic engineering, it might be based entirely on bandwidth and not have the latency scaler. That's great if you need to do that in your entire network, but we only needed to do this in a portion of our network. Again, band-aids, not body casts. Okay, so Flex Algo is really good for certain things, and we are probably going to use it for some other things like network overlays and stuff like that. But for this particular use case, it wasn't very useful. I've already talked about OpenFlow as well. Sort of my snarky remark about OpenFlow is that I wanted to only reinvent one of the wheels on the car I was driving, not all four of them, plus the engine, plus the Landau roof and the Corinthian leather seating area. In other words, OpenFlow lets me build pretty much entirely new forwarding algorithms from the ground up. That's great. That's not what I need. And I also talked about how OpenFlow programs state into the entire network. And we wanted to be able to program the packet. That's sort of the classic view of why segment routing instead of OpenFlow. And I talked about that last week. So there's also that aspect of it. You might also say, well, what about like doing some really cool AI machine learning stuff? And that's awesome. We don't really have anything that's completely shovel ready yet. Um, at least not 2 years ago. We're getting there. As I'm speaking, some of my colleagues and some of the people on this talk are actually doing work around this about building controllers that can do more predictive traffic engineering. I think it's going to be awesome when that happens. And what I'm really trying to do here is really kind of build the groundwork, build the foundation in a segment routed data plane that can actually make. So we actually have on controllers algorithms to actually make that stuff work pretty well. But again, I had to do this 2 years ago. So what did I do? I did segment routing, and particularly SRTE with weighted ECMP. Okay, so the idea there is I create a bunch of tunnels where the costs are all the same, but then I take another layer and I apply weights to each of those similar costs. And that weight acts like a percentage of traffic that it forwards over. So it's basically a weighting of the hash buckets when you hash traffic across ECMP links. Again, this doesn't require an offline controller. Spoiler alert. We're not going to be doing any kind of PCE or anything. And that turned out that was the requirement because, again, it wasn't working 2 years ago and we still don't have it working and we needed to do this then. So again, it had to be shovel ready. So what we're actually doing here is, if you look at this rather stylized version of it, we're creating a set of paths from a series of domestic routers and domestic routing locations that take a particular transatlantic link. And then we ECMP each of these. So each of these four links, in this case, there are really six now, has an equal cost. And then we weight them differently. So the blue link might be weighted more than the orange link or vice versa. And the important thing to understand, though, is that this is a loose path going to Boston. So any ECMP that's happening inside here, because, say we may have, links like that between like Chicago and Boston, that gets taken advantage of. We get to mux over those ECMP links. So we really have two layers of ECMP working here. The tunnels themselves are ECMP'd across each other, and then within each other, we have ECMP. So how do we do this? In this case, we're defining a path, and we're going to take a loose path to Boston. And then once we get to Boston, we're going to take a particular path across the pond. Now, that's actually useful to have both of those because in Boston, we have three different links that go across the pond. One's 100 gig, and now there are two that are 400 gig. That's not in the picture. Those were the dotted lines in the picture, but they weren't finished yet 2 years ago. They are finished now. So in this case, I have a path. This is going to take one of the links. I think this might actually take the 100 gig path. And I can also do this. I can do this with IP addresses. If I do with IP addresses, again, v4, I need to use v4 here for the reasons I already specified. But if I do this with IP addresses, what happens is that it resolves it to labels. And it basically, the router automatically resolves it to these labels. I do this for illustrative purposes, but basically, this label says, is the node SID, says take a loose path to Boston, and then take a specific interface across the pond, and then take this loose path to CERN. That's essentially what these labels say here. I define that path, and then I define a bunch of other paths, and then I embed them in LSP templates. So in this particular case, I create an LSP template, and then what I do is I stick not just CERN routers, but I've actually now stuck all the European routers into a policy that says generate LSPs based on this policy. And Nokia has this really cool feature called auto LSP that lets you do that. I assign a metric of each of these, and you can see from these different ones, this is path 1 and path 3, they have the same metric, but they have different weights. Weight 4 versus weight 18. The rest of this is obviously unique to segment routing. I'm specifying how many labels I want to be used for both fast reroute or TI-LFA, which I showed you last week, how that works. And then this is what I want to be able to set aside for my path labels. So you can see there are some limitations on what I can do in terms of label stack. But because I'm using a mix of strict and loose paths, I don't need to specify the label stack all the way across. I don't care. I want it to get to Boston, and then that's the only place where I need the traffic engineering. So once it gets to Boston, I want to tell you to take this one link. So that's really all I need to do. Again, Band-Aids, not body casts. And then I also I'll tell you what this BFD template is in a couple of minutes. When I do that, it creates a tunnel table. And I've told you I've done 6 of these now. So I've done 6 paths instead of just 1 and 3 that I showed you. And it creates in my tunnel table. I've already told you what these numbers mean, but I remind you that this is the tunnel metric. And so 9,000 is what I've set the tunnel metric to be. It's all the same. The IGP generated metric, which is embedded in both the SRISIS, remember this is actually SRISIS and this is LDP. That's 14,066. It actually doesn't matter if I set the tunnel metric to 15,000 on each of these, because the tunnel table preference is lower here. Remember I told you what that was? Tunnel table preference is 8. Here's a V6 version of it. So because I've set the tunnel table preference, these types of tables, SRTE, will take precedence over any other types of tables, any other types of tunnels in the tunnel table. Okay, and the reason for that is obviously I want my traffic engineered tunnels to take precedence over my non-traffic engineered tunnels, because again, I'm only using traffic engineering where I need it. So I can let the place where there's an absence of traffic engineered tunnels use the regular shortest path tunnels. Okay, this is what happens when I put this into the routing table. It's resolving the next hop using this SRTE tunnel, and we've got 6 different SRTE tunnels, which means we now create 6 different routes. These routes look the same because the next hop is the same, but it turns out I'm using a different tunnel for each of them. So the resolved next hop is different in each case. It resolves to a different tunnel. And if I look at this, there's the V6 version. If I look at the V6 version here in the miracle of extensive view, it actually shows me the ECMP weight for each of these routes. Okay, so there's my routing table. And that's what goes into my forwarding table is this weighted ECMP. And so that tells me how to hash the traffic across the different links. So does it work? Well, here's what it looked like in December when I gave this talk. There's more links now. Out of NUI 32 A of A, there's 3 more 400 gig links coming out of it. And this actually doesn't show the 2 near links we have. We have 1 near link that goes to London and 1 near link that goes to Amsterdam. But in this case, you have 3 400 gig links and then a bunch of 100 gig links. And then we've now upgraded these Europe links to 400 gig. They're now actually 2 by 400. So we have a little bit more bandwidth to play with here. And what I'm going to show you is our Stardust dashboard. Our Stardust dashboard sort of shows you what happens when You overlay SNMP information with NetFlow information. And again, this is why I really like being able to do ECMP at layer 3 rather than doing lags, because I can actually see the NetFlow going over each individual link that's in that physical ECMP group. There's a little bit of caveat here that needs to be shown. Obviously, this is sampled net flow. So these little stacked graphs here, those show you net flow information. This is actually very low resolution SNMP. So it's done just to render the graph really quickly. I'm just looking at order of magnitude here. And obviously you can see that there's some skew in here, and that has to do with how we measure net flow on ingress, also with sampled net flow. So the net flow doesn't quite add up to all of the SNMP here, but it gives me a good order of magnitude of what's going on. And so when I take my net flow information and I look at the averages, and when I copied and pasted these graphs into this, this is back in probably November when I did this. I happened to notice that, oh, this CERN to Vanderbilt, it's using a fair amount of bandwidth. I mean, it's not a lot, but it's using on this link average over 24 hours of 2.05 gigabits per second and peaking at 5.74. And on this other link, which is Boston to London 400 gig, which I'm weighting heavier, it's pretty much double that. Well, that's kind of cool. All right, so that's working pretty well. And then here's a 100 gig link, and so I have this weighted a lot lower, but I still see that CERN to Vanderbilt again. Okay, at about 900 megabits per second, and so on. Now here I go to my this is one of my nearer links. Okay, and I don't have this in in my tunnel mesh right now. And you see there's no CERN to Vanderbilt in here. There's a few other things that are here, and they're just sort of taking IGP paths to get across here. You can see at this point in November, we weren't using very much of this link. Um, and so I wasn't, so that link didn't really play into it, but that's because I didn't program that link to have a play in what was going on. Here I have another 100 gig link, and here we go. Now CERN to Vanderbilt is back because I put that link in the tunnel mesh. Again, here we are, CERN to Vanderbilt in the tunnel mesh. And I accidentally copied and pasted the same graph twice and did a little slide error. But there's another link in there. And trust me, there's also CERN to Vanderbilt traffic there. This is what the trace route looks like if you try to go from Nashville, which is very close to our Vanderbilt peering, and take it to that first sonar node. And you can see right around pretty much early on, we start splitting our traffic off. So the traffic starts balancing between an eastern path that goes to Atlanta and a northern path that goes to Equinix Chicago. And then from there, we split off to a bunch of different links, a bunch of different transatlantic links, and then it kind of blows up around here. So you can actually see it starting to balance a little bit. And then this, I decided, after I was looking at those graphs, I said, I wonder if it's actually following my weights. So I said, let me add up the weights of all of my links that I've configured here. Let me add up that average traffic that you saw in those graphs. And it actually turns out these two were the same. I did not duplicate that. These are actually roughly the same. And you can see what the weights are here. And so then I decided, okay, I'll use division technology and create a percentage out of each of these. And I created what the percentage was of the actual traffic and then of my desired weights. And it's uncanny. I mean, I was like shocked. This is the first one I tried, and I was like, all right, I'm quitting now. I'm not going to look at any of the other ones because this is so close to what I want. Now, there's a lot that comes out in the wash here. This is net flow. It's sampled net flow, so it's very statistical here. And also be aware that this is sampled out over 24 hours. In addition, the technology that Vanderbilt is using to get its traffic from CERN, and by the way, I got this wrong. It's actually CERN to Vanderbilt, not Vanderbilt to CERN. But the opposite direction is similar. But in this particular case, the traffic between Vanderbilt to CERN is using FTS, which is sort of a WebDAV with a lot of manipulating database stuff running around it that basically muxes out a lot of data into many, many flows. And these are WebDAV flows that run over port 8443. And so when you have lots of flows over the course of 24 hours, it's going to really balance your traffic out nicely. Like I said, a lot of this comes out in the wash. So this is one of the reasons why it looks so good, is basically because the traffic has just traffic is very amenable to this kind of load balancing. So that's good. It turns out that X-route D traffic is also really good, and a lot of the other mechanisms we use to transfer LHC data back and forth across the Atlantic is also very amenable to this form of traffic engineering. So that worked out really well for us. When we look at MTR, we're going to show you this is an MTR version of this is actually a little bit more complicated because this is coming from the West Coast. So what you can see here is I have a bunch of node SIDs, and I have an entropy label thrown in here. And then I have a few node SIDs, then I have my adjacency SID. So this is one of the nice things about having static adjacency SIDs and node SIDs that are out of different blocks, because now I can see which one's adjacency, which one's a strict interface that I'm using, and which one is basically just a loose path to a node, to a router loopback effectively. And so you can see here, I have a few node SIDs on this one. What am I trying to do there? Well, if you look at the ESnet map, you can see that from the West Coast, and that's where this is from, you can see this is coming from LBL. Okay, from the West Coast, I have a sort of middle northernish path and a southern path. And I decided I want to take use of both of those paths. Normally from the West Coast, I would only use the northern path. But in this case, I actually do some of my paths mucked down into the southern path as well. And so that's why I have those node SIDs program. What I basically said is go to Houston and then go to Atlanta, and then go to your transatlantic router and then take this specific transatlantic interface. That's good enough to steer the traffic along this southern path. If one of those Houstons or Atlanta, one of those goes down, or if something in between goes down, the path will still route around. So it's still a loose path. It'll still route around. It's not going to be reliant on one particular link. And again, it will use ECMP to get to those different destinations. So again, here you have, basically saying go to these different sub destinations as I take you to Boston or London or wherever, Boston or Washington or wherever we go in order to cross the pond. Okay, so that's all well and good. Now you may be asking yourself, here are our links, and again, this is different. These dotted links are now in production, and there's now even more links coming out, like I said, of NUI 32 A of A. But what if any of these goes down? I'm specifying an explicit link hop. I'm spacing take this link. What if that link goes down? And that's kind of an issue with segment routing is, first, we know TA links never go down. Transatlantic links, there's never boats dragging their anchors. There's never sabotage. There's never like an AMP site that gets flooded in Valencia or anything like that. So if it does go down, though, in that rare event, that's a little bit of an issue because segment routing, remember, is stateless. So when I program the label stack on it, if you go back to the trace route, you see these label stacks here. The router here, LBL59, that's pushing that entire label stack onto the packet has no way of knowing if this interface is up or not. It doesn't know whether it's up or not, okay? So what happens? It sends the packet out over that path, and then it just gets dropped on the floor when it hits that interface, potentially. Or potentially the router tries to send it around some other path that's not optimized. So in the case where if this link were to go away, because the whole point of the tunnel is to use that particular link, I just want to shut down the tunnel and use the other 5 to steer the rest of the traffic. So how do I do that? The answer is SBFD. Now, okay, if you know what classic BFD is, and I'll explain it to you in one slide with this clever analogy of the 2 spider persons pointing at each other. BFD is, now the acronym BFD means a lot of different things like Berkeley Fire Department or Bradford Regional Airport in Pennsylvania, but it also means bidirectional fault detection. And it is used on usually point-to-point links between 2 routers to basically figure out, make sure that if there's either a unidirectional loss of signal or if the link goes down due to some fault, it takes it out of routing very quickly. So you don't have to wait for the routing protocol to reconverge in order to pull that link out of routing, or you don't have to wait for like hello timers to expire, things like that. And the way it does this is by sending a continuous stream in each direction. So each of those spider people is pointing at each other. That's a continuous UDP stream. It's asynchronous in that it's not like a ping and a response. Okay, I'm just sending you the stream and I'm looking at your stream. If your stream stops, I still keep sending my stream. But if I don't see your stream, then that's when I shut down the routing protocol. But I still keep sending my stream of UDP packets at you. So I don't stop pointing no matter what. If you stop pointing, then I shut down the routing protocol on the link, not the whole link. So I just want to get traffic off the link, not actually shut down the link. Now, SBFD, I use actually a reflector. So this is sort of like a ping and a response. What I do is I program a packet the same way I program the regular traffic packets. So I program that packet with the label stack that I want it to take, that I want my regular traffic to take, my production traffic. And then I send that packet out. And then I wait for an answer back. The answer just comes back via the shortest path. It doesn't come back the same path because remember, segment routing only works in one direction. So I have to program packets in both directions. And in that little sort of spirograph display I showed you, I actually do that. You can't see from that map that that's what I did, but I actually do have the traffic being programmed in both directions. But for each SBFD session, I only care about one of those two directions. Okay. So the SBFD session is established. It sends a packet that's programmed according to the way I want it to. And then I get a response back that just comes back via the shortest path. I don't care what direction the response comes back. Think about it this way. You're sending your kid off to grandma's house and you write down the whole itinerary for your kid. They're going to have to take a bus to the ferry, to the train, then maybe get like an Uber Lyft when they get to the train station over by grandma's. You want to make sure they got there. You don't need grandma to retrace their steps and come back and tell you they got there. You need just grandma to call you and say, yeah, they got here. Okay, so that's basically what SBFD does. So it has a mechanism to do that called a discriminator, and this is just sort of gives you an idea of how you configure SBFD so that I can basically say I want to go to this particular router and I want it to be able to reflect this particular path back to me. It's basically specifying who grandma is in this particular case. And so that is something that's also embedded in our IGP. So um, it's another example of how a lot of this stuff we can just basically stick into the IGP and let the IGP handle it. The IGP becomes a very useful transport layer for all of our traffic engineering information that we need. From that point, it's a very easy configuration. In this case, I've configured it for 1,000 milliseconds or a second each with the multiplier of 3, which basically means that it takes 3 seconds to bring the link down. Okay, that's better than nothing, like never bringing the link down and dropping the traffic. 3 seconds is still a lot. That's still going to maybe cause some disruption, but it will not black hole traffic permanently. And so that's one of the good things. There'll be a good chance for things to recover. One of the reasons I do 3 seconds is because of the latency between, like say Sunnyvale and CERN is pretty high. It's going to be in the 100 to 200 milliseconds. I don't want to have problems where if there's, for whatever reason, a longer latency path forms or there's some little delay in getting the response back, I don't want to start flapping my tunnel a lot. There's also a hold down timer here, so it will hold it down for about 30 or 40 seconds, just so that it doesn't get real. If it is flapping, you don't get that flappiness causing problems for your actual traffic and the traffic you're trying to engineer across. So that's why I put this BFD template. I embed that SBFD template into my configuration for each LSP that I create. That means every time it creates an LSP, it creates an SBFD session. And then obviously BFD enable, for whatever reason, I have to tell it, yeah, I'm configuring this BFD and yeah, I want you to use it. And then what I say is failover action is failover or down. There is no failover tunnel here. I just want to bring the tunnel down. And then I use the other 4 tunnels or 5 tunnels that I've got in my ECMP group to route the rest of the traffic. So I just want to shut it down and shunt off the traffic to the other tunnels. Now, I love this. Here's what an SBFD packet looks like. Now, this is in our lab, so we use RFC 1918 addressing for our lab loopbacks. But look at the destination of this packet. That's not even RFC 1918. That's flat out bogon, okay? And so what that means is it's part of the loopback group. But what that basically means is um, I am forwarding this packet via an MPLS label. Okay, and so here you can see the MPLS labels that I'm using to go between these two routers in our lab. If for some reason those labels don't work, or they're incomplete, or something's not right, then I want to make sure that that packet has no chance of getting there. So if I've got some do-gooder Boy Scout router that's trying to send the packet on, say, well, I'll just decapsulate this and try to send it over regular IP, you're going to see this and it's going to say, oh no, that's a bogon. I'm throwing it on the floor. Because I don't want the packet to get there if production traffic can't get there along the path that I want it to take. So that's why I do SBFD that way. I shouldn't say I do it. That's why they designed SBFD to work that way. And you can see IPv6 is just as weird. Okay, it's this quad F plus, again, the old IPv4 loopback space, something that's not going to be forwardable. And that's really what they want to do. Now, the trip back is regular plain old unicast. Unicast UDP, I just sent it back. Here's the source port 7784, destination port, standard thing, and you can see I'm not using MPLS to send it back here. I'm actually just sending it back via IGP shortest path. So that's grandma calling you and saying, yeah, your kid got here, basically. Okay, so SBFD provides the fault tolerance, or really the fault notification, that tells the router, this tunnel doesn't work, so don't use it. And it allows me to safely and reliably use these ECMP meshes of tunnels that ECMP across the tunnels. And also, because I'm using segment routing and SRTE and not RSVP, I do ECMP within each tunnel as well, where I want to. In the case of the actual transatlantic link, that's not ECMP, except in one place where it is. Remember, I left you with the cliffhanger here last time, and I showed you how this has two node labels. Okay, so I just did this in about 2 weeks ago. I put this into production because we put new spectrum links on our New York router. So now we have 4x400 and 1x100 going from New York to London. Because we have so much bandwidth, I decided I'm not going to create like 5 tunnels that are all going to go through New York. I'll create one tunnel and then have the IGP do the rest of the ECMP from New York to London and then on to CERN or wherever it's going to go. So I'm going to stop sharing because I have this I'll just show you what's happening here in another window. And that other window is somewhere around here. Let me find it. I do have it in another window. Okay, so let me reshare this window. And this is also from our Stardust mesh. And okay, again, this is similar to the graphs that I showed you before. I basically use this dashboard to show all of my traffic engineering stuff. What you can see down here is these are our new spectrum links. This is an older lit service, but it's also 400 gig. And what I'm doing is with that one tunnel, I'm offloading about 20 gigabits per second of traffic. There's also some other tunnels that are using some of these links for Oscar circuits and things like that. But it basically spreading about 20 gigabits per second across these 4 links. And plus, I'm also spreading that across this London link here. So again, that's the beauty of being able to take segment routing and use sort of embedded ECMP with it, because I've got basically 5 links now that are ECMPing with one tunnel. So now it's not perfect because I'm ECMPing equally between the 100 gig shared link here and also between these 400 gig links. So there's some a little bit of tweaking that needs to be done there, but you can kind of see how this works when you just specify node SIDs like that. It takes advantage of a lot of the capacity we now have just turned up between, in this case, London and New York. So uh, that is largely my presentation. I do have one more slide, which is basically this here. Okay. Um, we don't know when it's to be continued. Obviously I love 70s TV, so uh, we don't know when this is going to be continued, but someday I hope to give another presentation to tell you all about the great things we did with our controller, because I've given you some very simple use cases that really only talk about like how you do things like relatively mixed, loose, and strict paths, but I don't really talk about how you use things like SR policies and binding SIDs and things like that. There's a lot more that segment routing can do in a lot more complicated use cases, but there's also a lot of really cool things you can do with these very simple use cases. And so that's kind of why I wanted to bring this part out and show you how you can do segment routing without a controller. So thanks a lot. I'm sorry I went a little bit over. I apologize for that.
No worries at all. So thank you so much for going through all of that, Michael. Um, I've just enabled it so that if people want to unmute and ask questions or, make snide comments, always welcome in this community. You can always raise your hand or put it in chat. We'll do anything. So I see Michael's already beat everybody to the punch. So go ahead, Michael Lambert.
Okay, Michael, in a network which does not already have MPLS, and given the current state of software on various routing platforms, would you recommend segment routing with MPLS or V6?
I think given the current set of software, I think that the work that routing vendors have done on getting SRv6 into a production ready state has been very good lately. And I would definitely consider SRv6 if you don't already have MPLS. I would definitely consider SRv6 to be probably the top candidate. The one consideration you have to give there is that because it uses IPv6 extension headers, you have to make sure that you carve out your ASN and your administrative boundary, that you don't let somebody leak SRv6 extension headers into your network. So one of the things that not all router vendors have implemented yet is the ability to block the SRv6 extension header at your perimeter if you don't want to do interdomain SRv6. If you do want to do interdomain SRv6, then you can certainly allow that to happen. But that's the one caveat that I would have there around SRv6 is you want to make sure that you administratively scope where you're doing your SRv6 correctly.
Okay, thanks.
All right. Do we have any other questions that people may want to ask? We'll point out that Davey has identified that as Rockford files.
Yeah, the first two were $6 Million Man. And who knew, by the way, that William Shatner was ever a guest star in $6 Million Man? I found that image. So now I'm dying to find that episode. I can't wait. It's kind of like when I saw the Columbo episode that had Patrick McGowan and Leslie Nielsen in it in serious roles.
Serious roles. Oh, okay. I have a hard time believing that's true. All right. Well, I think that you may have stunned everybody. Go ahead.
One other thing I want to say is a bunch of people send me email. I have not answered it yet. That is just because it's all in the queue to be answered. So I'm not ignoring you. Thank you very much for the email. Feel free to send me more. I'm going to go through and answer as many of the questions as I can. So thanks a lot for coming, and thanks very much for letting me give this talk, Jason.
Yeah, no problem. Thank you. We'll get the video posted and shoot me the slides as well. I'll make sure that those get posted. Next week's talk is going to be from Varden version from JLab, and he's going to be talking about EJ-FAT, which is, I'm sorry, EdgeFAT. I always say it wrong. It's a ESnet and JLab project for helping to sort of handle high throughput real-time data stream orchestrations. So a little bit different topic next week. Thanks everybody for tuning in, and we will talk to everybody soon.